Hi friends, this is Meenakshi. Today I am going to read the chapter named Phenol. Hope this video will help you. So let's start. Introduction. Phenols are the hydroxy derivatives of aromatic hydrocarbon in which hydroxyl group is directly attached to the carbon atom of the aromatic ring. Depending upon the number of hydroxyl group attached to the aromatic ring, phenols may be classified as monohydric, dihydric, trihydric, and polyhydric phenols, according as their molecules contain 1, 2, 3, or many hydroxyl groups respectively. For example, phenol. This is a monohydric alcohol. Orthocresol is also monohydric. Risocresol dihydric, pyrogalol trihydric. Simple phenol C6H5OH is used as an antiseptic as well as a disinfectant. As disinfectant, it is used to kill microorganisms present in the drains, toilets, floor, etc. Hexachlorophene, which is phenolic compound, is an active constituent of several mouthwashes, deodorants, soaps, and medicinal skin cleansers. Many phenols and phenolic ether occur in nature. Some of these are used in the manufacture of perfumes and flavors because of their pleasant odors. Thymol is a typical flavoring ingredient of thyme and mint is widely used in the preparation of mouthwashes because of its flavor and antiseptic property. Clove oil contains a phenol, eugenol, and is used by dentists as an antiseptic. Vanillin present in oil of vanilla beans is used as a flavoring agent in many confectionery items. For example, here the structure of different compounds are given like hexachlorophene, thymol, eugenol, or vanillin. Nomenclature of phenol. A monohydric phenol. The general formula of monohydric phenols is AROH, where AR is a phenyl, substituted phenyl, or any aryl group. These are named by following two systems. Common system. In the common system, the simplest member of this family is called phenol. All substituent phenols are named as derivative of phenol. The position of substituent on the aromatic ring with respect to OH group is indicated by prefix such as ortho, meta, para. In spite of these, some phenol are still best known by their trivial names. IUPAC system. In the IUPAC system, the simplest phenol is called benzenol, but all substituted phenols are named as derivative of phenol. Here, the position of a substituent with respect to OH group is indicated by Arabic numeral with carbon carrying OH group being numbered 1. Common and IUPAC name of some phenols are given below. 2-methyl-phenol, common name orthocresol. 3-methyl-phenol, common name metacresol. 4-methyl-phenol, common name paracresol. Benzenol has a common name phenol. 2-bromophenol, ortho-bromophenol. 3-aminophenol, meta-aminophenol. 4-nitrophenol, para-nitrophenol. As I have read it, the common as well as IUPAC name of different compounds. Now, phenol containing a carbonyl group such as aldehydic, ketonic, carboxylic, and or an ester group are named as hydroxy derivative of the parent aromatic compound. For example, 2-hydroxybenzaldehyde, 2-hydroxybenzoic acid, 4-hydroxyacetophenone, methyl 3-hydroxybenzoate. Dihydric and trihydric phenol. In the IUPAC system, simplest di, tri, and polyhydric phenols are named as benzene diol, benzene triol, benzene polyol respectively. These are also named as hydroxy derivative of benzene. However, they are better known by their trivial names. For example, 1,2-benzene diol is known more famously by catechol. 1,3-benzene diol is risocrinol. 1,4-benzydiol hydroquinone or quinol. 1,2,3 benzene triol pyrogalol. 1,2,4 benzene triol hydroxyquinol. 1,3,5 benzene triol phoroglucinol. 1,2,3,4,5,6 benzene hexol, simply benzene hexol. Structure and bonding in phenols, the OH bond is formed by overlap of sp3 orbital of oxygen with 1s orbital of hydrogen, while the CO bond is formed by overlap of sp3 orbital of oxygen with sp2 orbital of carbon of the benzene ring. The COH bond angle in phenol is 109 degree, which is slightly more than in methanol 0.8 sorry 108.5 degree. The CO bond length in phenol is however slightly less 136 picometer than in methanol 142 picometer. This is due to resonance, as a result of which the carbon-oxygen bond acquires some double bond character because of conjugation of lone pairs of electron of oxygen with benzene. Since the oxygen atom is more electronegative than both carbon and hydrogen, the electrons of the carbon-oxygen and oxygen-hydrogen bond are little more displaced towards the oxygen atom. As the result, electron density near the oxygen atom is slightly higher than near the carbon and hydrogen atoms. In other words, phenol molecule is dipolar in nature, with the oxygen carrying a partial negative charge and carbon hydrogen carrying partial positive charge. This is supported by the fact that phenol has a dipole moment of 1.54. Dipole moment of phenol is however lower than methanol 1.71. This is due to reason that carbon oxygen bond in phenol is less polar due to electron withdrawing effect of the benzene ring, while in methanol CO bond is more polar due to electron donating effect of CH3 group. Due to this dipolar nature, phenols form hydrogen bonds. Methods of formation. Some important general methods of preparation of phenol are described. Alkali fusion of sulfonates. Phenol are produced when sulfonic acid or their sodium salts are fused with NaOH at 300 to 350 degrees Celsius at 573 to 623 Kelvin, followed by acidification. Limitation. The main disadvantage of this reaction is that fusion is usually carried out at high temperature, which leads to the undesirable side products also. This method cannot be applied to salts of sulfonic acid containing substituents such as COOH, Cl, NO2, which often give side reactions. Hydrolysis of diazonium salts. This is one of the most convenient method of preparation of phenol. When diazonium salt solution is added to boiling dilute H2SO4, phenols are formed. Arene diazonium salt reacts with water in presence of dilute H2SO4 and heat gives aromatic benzene ring carrying OH, that means simply phenol, plus HCl plus N2. Benzene diazonium chloride plus H2O reacts again with dilute sulfuric acid and gives phenol plus HCl plus N2 from aryl halides. Chlorine in chlorobenzene is inert to nucleophilic displacement under usual conditions. However, when chlorobenzene is heated with 6 to 8% NaOH solution, At 623 Kelvin under 320 atmosphere pressure, it forms sodium phenoxide, which upon acidification with dilute HCl gives phenol. Chlorobenzene reacts with 2NaOH at 623 Kelvin 320 atmosphere gives NaCl plus H2O, and the products will be sodium phenoxides, and then it again reacts with HCl and form phenol. This method is called dose method and used for commercial production of phenol. Mechanism. This reaction is believed to occur via benzene mechanism as depicted below. Chlorobenzene reacts with NaOH 6 to 8% at 623 Kelvin 320 atmosphere and forms the intermediate benzene. And ultimately it reacts with NaOH. By the removal of water, it forms sodium phenoxide. However, if the halogen in the aryl halides is activated by the presence of strong electron withdrawing group such as NO2 at ortho para position, then the halogen can be easily displaced by heating in aqueous solution to give the corresponding phenol. For example, P parachloronitrobenzene plus 2 NaOH 15% NaOH at 433 Kelvin. It reacts and ultimately it gives para-nitrophenol. 2,4-dinitrochlorobenzene. It reacts with aqueous Na2CO3 and sodium carbonate at 403 Kelvin and dilute HCl. It gives 2,4-dinitrophenol. 2,4,6-trinitrochlorobenzene reacts with water at 323 Kelvin. It gives 2,4,3-trinitrophenol. Is commonly and very famously known by the name picric acid. It may be noted here that as the number of nitro group with respect to halogen atom increases, the hydrolysis becomes easier and easier and is evident from decrease in severity of conditions employed. From isopropyl benzene cumene. Phenol is prepared commercially from cumene to phenyl propane or isopropyl benzene, which in turn is prepared by Friedel-Crafts alkylation of benzene with propane in presence of phosphoric acid. This upon aerial oxidation formed cumene hydroperoxide, which upon subsequent hydrolysis with an aqueous acid give phenol and propanone or acetone. Benzene in the reaction here reacts with propene in presence of phosphoric acid at 523 Kelvin and pressure Friedel-Crafts alkylation. It forms cumenes and then by aerial oxidation it forms cumene hydroperoxide. By adding then dilute H2SO4 at 323 and to 363 Kelvin, phenol plus propanone or acetone is formed. Mechanism. The entire process involves the following three reactions. The first reaction involves Friedel-Crafts alkylation, in which the isopropyl carbocation generated by addition of a proton to propene attacks the benzene ring to form cumene. H3PO4 gives H positive plus O negative PO3 H2O. Propene reacts with H positive gives isopropyl carbocation, and then by going electrophilic substitution reaction in presence of benzene it gives cumene. The second reaction involves the conversion of cumene into cumene hydroperoxide. It is an auto-oxidative reaction which is carried out in presence of radical initiator. The reaction occurs in free radical chain mechanism. Initiation. Cumene reacts with radical or initiator and it forms tertiary benzene radical. Then ultimately, after reactions in many steps, it forms cumene hydroperoxide. The third reaction involves acid catalyzed arrangement of cumene hydroperoxide to phenol acetone. It occurs by the following steps. Cumene hydroperoxide 1 accepts a proton, step 1, to protonated cumene peroxide 2, which loses a molecule of water, step 2, to form an intermediate 3 having electron deficient oxygen atoms. Since phenyl group has greater migratory aptitude than methyl group, therefore migration of phenyl group to electron deficient oxygen atoms, step 3, generates a carbocation, step 4, which is stabilized by resonance. Nucleophilic attack by water on carbocation generates a heavy ketone while undergoing acid catalyzed hydrolysis to form phenol and acetone. Cumene hydroperoxide reacts with H positive, step 1, and it forms CCH3, C6H5CH3O, OH2 positive. Removal of H2O is second step. 1 to phenyl shifts occurs, and at the fourth step and fifth step, hemiketal is formed, and ultimately it forms acetone plus phenol. By decarboxylation of phenolic acid. Decarboxylation of phenolic acid by distillation with soda lime NaOH followed by acidification with dilute HCl gives phenol. For example, dilute sodium silicate gives sodium silicate reacts with 2NaOH in presence of calcium oxide and heat. It gives sodium phenol. Dilute HCl and it ultimately forms phenol. From Grignard reagents, when oxygen is bubbled through ethyl, ethyl solution of an aryl magnesium halide, it gives an addition product which upon hydrolysis with dilute mineral acid gives the phenol. From coal tar, phenol and cresol are isolated from middle oil section 243 to 503 Kelvin of, of coal tar distillation. Physical properties. Physical state. Pure phenols are either colorless liquids or solid, but they are usually brown due to atmospheric oxidation. Boiling points. Like alcohol, the boiling points of phenol are also much higher than the aromatic hydrocarbons and haloarenes. Benzene has a boiling point of 353 Kelvin. Bromobenzene has 439, chlorobenzene 405, and phenol 455. This is again due to the reason that phenols, like alcohols, also form intermolecular hydrogen bonds shown below. Thus, phenols, like alcohol, exist as associated molecules. Solubility. Like alcohol, phenols also form hydrogen bond with water and hence should be soluble in water, but the solubility of phenols in water is much lower than that of alcohol because of larger hydrocarbon part or benzene ring present in their molecules. However, phenol itself and some di and trihydrophenols are fairly soluble in water. Further, due to large hydrocarbon part, phenols are soluble in organic solvents such as ether, alcohol, etc. Apart from intermolecular hydrogen bonding, certain substituted phenols such as fluorophenols and nitrophenols can also form intramolecular hydrogen bonding. For example, orthonitrophenol, due to proximity of OH and NO2 group under chelation, it forms intramolecular hydrogen bond, while metaparisomers forms intermolecular hydrogen bonds. As the result, orthonitrophenol exists as a discrete molecules while meta and para isomer exist as associated molecules. Consequently, orthonitrophenol has lower boiling point and meta para isomers and hence is seem volatile. Further, due to chelation, orthonitrophenol cannot form a hydrogen bond with water, whereas metaparisomers can. As a result, solubility of orthonitrophenol in water is lower than that of metaparisomers. Acidic character of phenols. Phenols are weakly acidic compounds. They turn blue litmus red and also reacts with aqueous alkalis to form phenoxides and phenates. Alcohols neither turns blue litmus red nor reacts with NaOH. This test distinguishes phenols from alcohol. These reactions suggest that phenol are stronger acid than alcohol. However, phenols are weak acid than carboxylic acid or even carbonic acid. It is because of this reason that phenols do not decompose carbonates and bicarbonates using CO2 gas. Instead, phenols are precipitated from aqueous solution of phenoxide by bubbling CO2 through them. Explanation for stronger acidic character of phenol than alcohols. As stated above, as phenol are stronger acids than alcohol, this appears rather surprising since both alcohol and phenol contain same OH group. In other words, what is the reason that an OH group attached to a benzene ring is much more acidic than the OH group attached to an alkyl group? To answer this question, let us compare the stability of ion left after removal of proton and stability of unionized compounds. Phenols may be considered to be resonance hybrid of following structures. As the result of resonance, oxygen atom acquires a partial positive charge. This weakens OH bond and thus facilitates the release of proton. Phenoxide ion thus formed also exists as a resonance hybrid of structure 6 to 10. Thus, both phenol and phenoxide ion are stabilized by resonance, but phenoxide ion is better stabilized than phenols because structure 5 to 10 carry only a negative charge, but structures third and fourth involve separation of positive and negative charge. Hence, phenols also has a strong tendency to form more stable phenoxide ion by releasing a proton. However, in case of alcohol, both the alcohol molecules in alkoxide ion are represented by one structure each and there is no resonance. Alcohols more stable, alkoxide ion is less stable. Further, alkoxide ion due to the presence of formal negative charge on it has a greater energy and hence is less stable than alcohol molecule. Thus, alcohols have a negligible tendency to form less stable alkoxide ion by releasing a proton. Thus, we conclude that phenols are stronger acids than alcohols because of phenoxide ion left after the release of proton is stabilized by resonance, but the alkoxide ion is not. Effect of substituent on the acidity of phenol. As discussed above, the acidity of phenol is due to the greater resonance stabilization of phenoxide ion relative to phenol. Therefore, any substituent which stabilize the phenoxide ion more by dispersal of negative charge will tend to increase the acidity of phenols. Conversely, any substituent which destabilize the phenoxide ion related to phenol by in intensifying the negative charge will decrease the acidity of phenols. Electron withdrawing groups like NO2, CN, halogen which stabilize the phenoxide ion by dispersing the negative charge relative to phenol increases the acidic strength of phenols. Electron withdrawing group withdraws the electron, disperses the negative charge, stabilizes the phenoxide ion with respect to phenol and thus increase the acidic strength. Electron donating groups like NH2 or any alkoxy group or simply are alkyl which destabilize the phenoxide ion by intensifying The negative charge relative to phenol tend to decrease the acidic strength of phenol. Electron donating group donates electron and intensifies the negative charge, destabilize the phenoxide ion with respect to phenol, and thus decrease the acidic strength. Thus, in a nutshell, the electron withdrawing substituent increase the acidic character of phenol, while electron donating substituent decrease the acidity of phenols. Shows the effect of different substituent on the acidity of phenols. Value comparison of acidic strength of some phenols. Value of pKa. Phenol value of pKa for phenol at 298 Kelvin is 9.96. Orthocresol 10.21, metacresol 10, paracresol 10.18, catechol 10, resorcinol 9.52, hydroquinone 9.70, orthofluorophenol 8.82, metafluorophenol 9.28, parafluorophenol 9.95. And here the other side of the table shows the pKa value of phenols, different phenols at 298 Kelvin, like orthochlorophenol 8.11, metachlorophenol 8.20, parachlorophenol 9.20, etc. The acidic weakening effect of electron withdrawing groups and acidic strengthening effect of the electron withdrawing groups is more pronounced at ortho and para position with respect to OH group than that at meta position. This may be explained as follows. Both inductive and resonance effects influence the stability of phenoxide ion left after removal of a proton. In some cases, both inductive and resonance effects reinforce, while in other cases they may oppose. Whenever they oppose, either the inductive effect or resonance effect dominates depending upon the nature and position of substituent on benzene ring as discussed below. Resonance effect. Nitro group has a powerful minus I as well as minus R effect. Therefore, irrespective of the position of nitro group, all nitrophenols are stronger acid than phenol, although minus I effect decreases with distance. Minus R effect is more pronounced at ortho para position than at meta. To explain this, let us compare the stability of ortho, meta, and para nitrophenoxides. Here, the different resonating structures of orthonitrophenolxide ions are shown. It is evident from above structures that both ortho and para nitrophenoxide ions are stabilized by 5 resonating structures in one of the structures. In each case, one or two conjugation is extended up to oxygen atom of nitro group, but no such configuration is possible for meta-nitrophenoxide ion, and meta-nitrophenoxide ion are more stable at meta-nitrophenoxide ion, and hence orthonitrophenol and paranitrophenols are stronger acid than metanitrophenol. Out of orthonitrophenol and paranitrophenol, orthonitrophenol is less acidic than paranitrophenol due to intramolecular hydrogen bonding or chelation, which makes loss of proton little more difficult. Thus, the acidic strength of nitrophenols relative to phenol decreases in the order paranitrophenol greater than orthonitrophenol, greater meta-nitrophenol, greater than phenol. The further greater the number of electron withdrawing groups of ortho and para position, more stable is the phenoxide ion and hence more acidic is the phenol. Thus, the acidity of nitrophenols with respect to phenol decreases in the order 2, 4, 6 trinitrophenol greater than 2, 4 dinitrophenol greater than 4 nitrophenol or 2 nitrophenol or greater than phenol. Inductive and hyperconjugation effects. Comparison of acidic strength of halophenols. Halogen have both plus R and minus I effect, but the minus I effect predominates over plus R. Therefore, all halophenols except parafluorophenols are more acidic than phenols itself. Further, since minus I decreases with distance, therefore acidic strength of halophenols decreases in the order. Orthohalophenols greater than meta halophenols greater than para halophenols. However, in case of parafluorophenols, plus R effect and minus I effect of F almost balance each other, and hence it is almost as acidic as phenol itself. Amongst orthofluorophenols is weakest acid due to stronger intramolecular hydrogen bond. The acidity of other halophenols decreases as the minus I effect of halogen decreases. Thus, the acidity of orthohalophenols decreases in the order orthochlorophenol greater than orthochromophenol greater than orthoiodophenol greater than fluoro phenol. Comparison of acidic strength of cresol. Since alkyl group is electron donating due to the hyperconjugation effect, therefore all the cresols methyl phenols are less acidic than phenol itself. The hyperconjugation effect, like resonance, cannot operate at meta position. Therefore metacresol is more acidic than ortho and para. Out of orthoparacresol, paracresol is more acidic than orthocresol due to the filled effect, which makes the loss of a proton little more difficult. Thus the overall strength of cresols relative to phenol decrease in the order phenol greater than metacresol greater than para and greater than orthocresol. Comparison of acidic character of methoxy and aminophenols. A meta-methoxy and a meta-amino group can not enter into resonance with hydroxy group, but exert minus I effect from this position. Therefore, meta methoxyphenol and meta-aminophenols are more acidic phenols due to minus I effect of OCH3 and NH2 groups respectively. Since the minus I effect of OCH3 group more than that of NH2 group, therefore methoxyphenol is a stronger acid than meta-aminophenol. The strength decreases in the order meta-methoxyphenol greater than meta-aminophenol greater than phenol. In comparison of acidic character of dihydric phenol, catechol, resorcinol and hydroquinone. Resorcinol, the two OH groups are present at meta position and hence one OH group cannot enter the resonance with the other OH group. Instead, minus I effect of one OH group on the other makes resorcinol more acidic than catechol and hydroquinone. In catechol, the two OH groups are involved in the intramolecular hydrogen bonding chelation, which makes the loss of a proton little difficult as compared to that hydroquinone. In other words, hydroquinone is more acidic than catechol. Thus, overall decreasing acidity of dihydric phenols is resorcinol greater than hydroquinone greater than catechol. Reactions of phenol. Some of the important reactions of phenol ether formation, Williamson synthesis reaction. Sodium or potassium peroxides reacts with alkyl halides to form ethers. This reaction is called Williamson synthesis. Thus, Williamson synthesis is an SN2 reaction. Alkyl phenyl ethers can also be prepared by treating phenol with dimethyl sulfate or diethyl sulfate in presence of NaOH. Sodium methyl sulfate can react once again with second molecule of sodium phenoxide to form another molecule of anisole. Thus, 1 mole of dimethyl sulfate forms 2 moles of ether. Similarly, diethyl sulfate reacts with phenol in presence of NaOH to form phenetiol. Reaction of alkyl halides. Like alkyl halides, allyl halides also reacts with sodium and potassium salts of phenol to form allyl aryl ethers. Cleason rearrangement. When an allyl aryl ether is heated alone or in an inert solvent such as diphenyl ether at 475 Kelvin, It undergoes a rearrangement called Cleason's rearrangement to form allyl phenols. During this reaction, the allyl group migrate to ortho position, and if both the ortho positions are occupied, then it goes to the para position. However, in no case does it go to meta position. Depending upon whether the migration occurs to ortho or para position, the Cleason rearrangement is accordingly refers to as ortho rearrangement or para rearrangement. Ortho rearrangement. Allyl phenyl ether reacts at 473 kelvins and gives ortho allyl phenol. Para rearrangement. Allyl 2,6-dimethyl phenyl ether reacts at 473 Kelvin and it gives 4-allyl 2,6-dimethyl phenol. Mechanism of ortho rearrangement. This reaction does not require any catalyst and is an example of pericyclic reaction. It is concerted reaction which occurs through a cyclic transition state. In other words, the cleavage of allyl oxygen bond and the formation of allyl carbon bond at ortho position is asynchronous as shown here. The cyclohexadione diene intermediate one thus formed undergo tautomerism to form the more stable orthoallyl phenol. From the above mechanism, it is evident that during the rearrangement, it is the gamma carbon of the allyl group with respect to oxygen atom which gets attached to the ring carbon. In other words, during ortho rearrangement, alpha gamma bonds is reversed. This is supported by tracer studies. Thus, while when allyl phenyl reacts phenyl ether having carbon 14 tracer at gamma position was subjected to Cleason rearrangement, the rearranged product has carbon 14 tracer attached to the ring at the alpha position. Allyl phenyl ether having carbon 14 at gamma position is when heated at 475 Kelvin. It gives orthoallyl phenol having carbon 14 at alpha position. Similarly, when crotyl phenyl ether was subjected to Cleason's rearrangement, the rearranged product had a methyl group at the carbon atom directly attached to the ring. Mechanism of para rearrangement. Unlike ortho rearrangement, which occurs in one step, para rearrangement occurs in two steps. In first step, the ortho rearrangement occurs and cyclohexadiene intermediate to is formed, but this intermediate cannot undergo tautomerism since there is no hydrogen available at ortho position. Instead, it undergo another ortho rearrangement to give cyclohexadione, which, because of the presence of hydrogen, readily undergoes tautomerism to give para-allyl phenol. Thus, in para rearrangement, one inversion is followed by another inversion, and hence there is no net inversion in the position of substituent with respect to starting component. Ester formation acylation. When phenols are treated with acid chlorides or anhydrides in presence of pyridine, the hydrogen atom of OH group is replaced by RCO group to form esters. For example, here phenol reacts with propanoyl chloride in presence of pyridine give phenyl propanoid plus HCl. Phenol again reacts with acetic anhydrides in presence of pyridine gives phenyl acetate plus CH3COOH acetic acid. Benzoylation of phenols is usually carried out by the presence of aqueous NaOH since benzoyl chloride is not readily hydrolyzed by alkenes. Thus, phenol reacts with benzoyl chloride in presence of NaOH gives phenyl benzoate plus HCl. This reaction of phenol with benzoyl chloride in presence of NaOH is called Scotton-Bowman reaction. Ferri's rearrangement. When a phenolic ester is heated with anhydrous AlCl3, the phenyl group migrates from phenolic oxygen to ortho-para position, give the mixture of ortho-para hydroxyketone. This reaction is called Ferri's rearrangement. Phenyl acetate firstly reacts in presence of anhydrous AlCl3 and heat, and second there is an acidic condition. It gives orthohydroxyacetophenone plus parahydroxyacetophenone. Phenyl benzoate reacts with anhydric AlCl3 and acidic condition, it gives orthohydroxybenzophenone plus para-hydroxybenzophenone. In general, low temperature below 333 Kelvin favor the formation of para-isomer, while high temperature favor the formation of orthoisomer. The reason being that para-isomer is formed faster, kinetically controlled, but orthoisomer is thermodynamically more stable due to chelation in the intermediate product as shown. The mechanism. This reaction occurs in two steps. Since crossover products have been isolated when mixture of two identical but different substituted separated treated under similar conditions. For example, ester gives ketone 3 while ester 2 gives ketone 4. But the mixture of 1 and 2 is heated together with anhydrous AlCl3. Apart from ester 1, 2 and 4 crossover products 4 and 5 are also obtained. The reaction with zinc dust. Phenols, but not alcohols, when distilled with zinc dust, give the corresponding aromatic hydrocarbon. Phenol reacts with GNN in presence of wheat gives benzene plus sedano. Electrophilic aromatic substitution reaction. The OH group activate the benzene ring towards electrophilic substitution and direct the incoming group of to orthopara position. Thus, the phenol readily undergo electrophilic substitution reactions. The activation of effect of OH group is so strong that it usually substitution occurs. Explanation of orthopara directing and activating influence of OH group. The oxygen atom contains two lone pairs of electrons. One of its lone pair interacts with pi electrons of the benzene ring, thereby increasing the electron density at all the nuclear position of the benzene ring. But the increase in the electron density is much more at orthopara position relative to meta position. In other words, the aromatic ring gets activated and further electrophilic substitution is in the ring becomes easier than in the benzene itself. Further, since the electron density of oxygen orthopara position is more than meta position, then therefore further substitution occurs at orthopara position. Orthopara directing influence of OH group can be explained in terms of relative stability of carbocation resulting from ortho-meta para attack as discussed below. The carbocation resulting in the formation of orthotect is a resonant hybrid of four structure funny fundy. Out of these complete the structure 2b is particularly more stable than other because in each atom except hydrogen of course has complete octet of electrons. Similarly, the carbocation resulting from para attack is also a resonance hybrid of 4 meta attack is four structures of which structure 2C is the most stable. However, the carbocation resulting form of meta-attack resonance hybrid of only three structures 3A, 3C, and there is no resonating structure corresponding to structure 1B, 2C. This means that the carbocation result from orthoparattack are more stable than carbocation resulting from meta-attack. Therefore, electrophilic substitution in phenol mainly occurs at orthopara position. Halogenation. Phenol, when treated with chlorine or bromine water, gives polyhalogen derivative in which all hydrogen atoms present on ortho and para position with respect to OH group are replaced by chlorine or bromine atoms. Phenol reacts with 3Br in presence of water, gives 2,4,6 tribromo phenol, white PPT plus 3 HBr. In fact, the reactivity of phenol towards the halogenation is so great that even substituent like SO3H group, if present at ortho and para, are displaced by halogen atoms. Halogenation can, however, be stopped at monohalogenation stage if the reaction is carried out in presence of non-polar or less polar solvents such as CS2, CS3, Cl, CCl4 at low temperature. For example, phenol reacts with Br2 in CS2 at 273 Kelvin. It gives 4 bromophenol major product 80 to 84% and 2 bromophenol a minor product. Reason in aqueous solution, the phenol ionized to form phenoxide ion due to presence of negative charge on oxygen atom. Phenoxide ion donates the electron to the benzene ring to larger extent as the ring get highly activated and hence twice substitution occurs. On the other hand, non-polar solvent, the ionization of phenol is greatly suppressed. As a result, the oxygen of OH donates electron to the benzene ring to only small extent. Consequently, the ring is activated only slightly and hence mono substitution occurs. Further, because of steric hindrance at the ortho position, the para substitution occurs usually predominates. Nitration with dilute nitric acid at 293 Kelvin. Phenols give some mononitrophenols and 2,4-nitrophenols. For example, phenol reacts with dilute HNO3 at 293 Kelvin, give 2 nitrophenol plus 4 nitrophenols. The ortho and para isomers can be separated by steam dilution since ortho isomer is a steam volatile due to chelation, while para isomer is not steam volatile due to the association of molecules by intermolecular hydrogen bonding. The yield of mono nitrophenols is quite low due to the partial oxidation of the ring by HNO3. However, if the phenol is first treated with nitrous acid, NaNO2 plus HCl, and then nitrosophenol thus obtained is oxidized with dilute HNO3, the yield of mononitrophenol is substantially increased. Phenol reacts with HNO3 at 280 Kelvin. NaNO2 plus HCl give 4 nitrosophenol 90%. Then it reacts with dilute HNO3 oxidation. It gives 4 nitrophenol. With the concentrated nitric acid in presence of concentrated H2SO4, phenol give 2,4,6 trinitrophenol. Picric acid. The yield is poor since most of the phenol is oxidized by concentrated nitric acid. Picric acid is, however, best prepared by first treating the phenol with concentrated H2SO4 at 373 Kelvin when a mixture of two phenol sulfonic acid and 4-phenol sulfonic acid is formed. The mixture is then heated with concentrated HNO3 to form picric acid in about 90% yield. During this reaction, nitration with simultaneous replacement of sulfonic acid group by the nitro group occurs. Phenol reacts with concentrated H2SO4 373 Kelvin gives 2-phenol sulfonic acid plus 4-phenol sulfonic acid. It reacts with concentrated HNO3 gives picric acid. Sulfonation of a phenol treatment with concentrated H2SO4 give the mixture of ortho and para isomer. If the sulfonation is carried out at low temperature, the ortho isomer predominate, and if the sulfonation is carried out at high temperature, para isomer is chief product. Friedel-Crafts reaction. Phenols, when treated with alkyl halide in presence of anhydrous ClCl3, undergo Friedel-Crafts alkylation to form alkyl substituted phenol. Usually, the para isomer is the chief product. Phenol reacts with methyl chloride in presence of anhydrous ClCl3. It gives 4-methyl phenol major and 2-methyl phenol minor. The yield of the alkyl phenols is generally low since AlCl3 coordinates with the oxygen atom. Phenol also undergo Friedel-Crafts acylation reaction with acid chloride and anhydrides in presence of anhydrous AlCl3 to form mixture of ortho-para hydroxyketones. However, the hydroxyketones or acyl phenols are better prepared by Ferri's rearrangement. Gutterman aldehyde synthesis or Gutterman formylation. It is a useful method for preparation of phenolic aldehydes. It involves the treatment of phenol with mixture of hydrogen cyanide and hydrogen chloride in presence of anhydrous AlCl3 to form corresponding aldehyde hydrochloride, which upon boiling with water undergo hydrolysis to give a corresponding phenolic aldehyde. Instead of phenols, the phenolic ethers can also be used in this reaction. The anisole reacts with HCN plus HCl anhydrous AlCl3. It gives aldamine hydrochloric fluoride. It reacts with H2O. It gives P anisaldehyd. The formyl group goes to para position with respect to OH. If this position is broke, it does go to ortho position. Mechanism. This reaction is an example of electrophilic aromatic substitution reaction in which the formaldyminium ion 1 formed by the reaction of HCN and HCl in the presence of anhydrous AlCl3 attacks the benzene ring to first give an aldimine 2, which upon subsequent hydrolysis with mineral acids give the corresponding phenolic aldehyde. Hobens-Husser reaction. It is an extension of Gattermann formylation reaction and involves acylation of highly reactive polyhydric alcohol having hydroxy group in the meta position with respect to each other. The reaction is carried out by passing dry acyl gas through cool ethyl solution of reactive phenol and alkyl cyanide in presence of aqueous zinc chloride or aluminum chloride. When ketamine hydrochloride is precipitated, this upon hydrolysis with boiling water gives the corresponding polyhydroxy ketone. For example, fluoroglucinol reacts with acetonitrile in an hydrocell Cl3. It gives ketamine hydrochloride boiling H2O. It gives 2,4,6 dihydroxy acetophenone plus NH4Cl. The mechanism of the reaction is exactly similar to Gattermann formylation reaction as shown. Carboxylation Kolb's reaction. Kolb-Smith reaction. Direct introduction of a carboxyl group into aromatic compound is called carboxylation. This is carried out by heating sodium salt of phenol with carbon dioxide under pressure. For example, sodium phenoxide when heated with carbon dioxide at 400 Kelvin under a pressure of 4 to 7 atmosphere followed by acidification gives 2-hydroxybenzoic acid as the main product A along with a small amount of 4-hydroxybenzoic acid. This reaction is called Kolb's reaction. Sodium peroxide reacts with CO2 at 470 Kelvin, 400 Kelvin and 4 to 7 atm gives sodium salicylate. It reacts with dilute HCl. It gives 2-hydroxybenzoic acid. Kolb's reaction is an important example of electrophilic substitution reaction. It involves the electrophilic attack by carbon dioxide on the phenoxide ion. Riemer-Tiemer reaction. The treatment of phenol with chloroform in the presence of aqueous sodium or potassium hydroxide at 340 Kelvin followed by hydrolysis of resulting Riemer-Tiemer reaction. Treatment of phenol with chloroform in presence of aqueous sodium potassium hydroxide at 340 Kelvin followed by hydrolysis of the resulting product gives 2-hydroxybenzaldehyde salicylaldehyde as the major product along with small amount of para-hydroxybenzaldehyde. For example, phenol reacts with CaCl3 in presence of NaOH at 340 Kelvin and H3O positive. It gives salicylaldehyde as a major product and para-hydroxybenzaldehyde as a minor product. This reaction is called Riemer-Tiemer reaction. The orthoisomer is separated by the para by the steam distillation. If instead of chloroform carbon tetrachloride is used, salicylic acid is obtained as the major product along with small amount of para-hydroxybenzoic acid. Mechanism. The Riemer-Tiemer reaction is an example of electrophilic substitution reaction. The electrophile in this reaction is a dichlorocarbene, which is obtained by action of alkali on the chloroform. Attack of dichlorocarbene on phenoxide ion results ultimately in the formation of benzyl derivative, which upon subsequent hydrolysis gives salicylaldehyde. The predominance of orthoisomer in this reaction is due to the greater stability because of intramolecular hydrogen bonding. Lieder-Manson's reaction. Phenol condensed with aldehydes in presence of an acid or a base catalyst. The product of these initial condensation reactions subsequently undergo polymerization to form polymers. For example, when phenol is treated with formaldehyde in presence of an acid or a base, it initially gives a mixture of ortho and para-hydroxymethylphenol 1 and 2. This reaction is called Lieder-Manson's reaction. The reaction does not stop here. The hydroxymethylphenol 1 and 2 thus form condensed with further amount of formaldehyde to form bis hydroxymethylphenol 3 and 4 or with further amount of phenol to form possible dihydroxy diphenyl methane 4, 5 and 6. Repetition of these condensation reaction at all the available ortho-para position of phenol ultimately leads to the formation of highly cross-linked three-dimensional structure polymer called bakelite. Mechanism of Leder-Manson's reaction. It is an example of electrophilic substitution reaction which involves electrophilic attack of formaldehyde on phenoxide ion or protonated formaldehyde on phenol described below. Here, it can occur in two ways, a base catalyzed or acid catalyzed reactions. As the mechanism of the reaction is shown here, similar mechanism can be written from the formation of para-hydroxymethylphenol. Phthalene reaction. On heating with phthalic anhydride in presence of concentrated H2SO4 on anhydrous sudden Cl2. Phenols are converted into phthalenes. For example, phenol itself under these conditions give phenolphthalein. Phenolphthalein is used as an indicator in acid-alkali titration. It is colorless and acidic in acidic medium but turns pink in alkaline medium. Coupling with diazonium salts. Benzene diazonium salt coupled with phenol in weakly alkaline medium at 273 to 278 Kelvin, giving colored substances called azo dyes. This reaction is called coupling reaction. Benzene diazonium chloride plus phenol weakly alkaline solution pH 9 to 10 gives para-hydroxybenzene. It is a orange dye. Distinct between alcohol and phenol. Alcohols can be distinguished from phenol by the following test. Litmus test. Phenol turns blue litmus red, but alcohols do not. The reaction with ferric chloride. Phenols react with natural ferric chloride solution to give blue, violet or green coloration, whereas alcohols do not. Coupling reaction. Phenol reacts with diazonium salts in weakly basic solution to form yellow or orange colored azo dyes, but alcohols do not. Bromine water test. Phenol on shaking with bromine water give white PPT of 2,4,6 tribromophenol, but alcohols do not. Thank you so much for listening.